Hello everybody. This project will explore the concept of cognitive radio. Presenters will be Cesar Barragan, Zaid Elias, and Diego Aguiar.
So, what is cognitive radio? In today's world, use of wireless devices has increased significantly with the advances in wireless technology. Because of this increase, a huge amount of spectrum is required to support this increasing number of wireless devices. If one was to check the current spectrum allocation chart, it's very hard to find free spectrum to support upcoming volumes of wireless devices and mobile data traffic. This is where cognitive radio can help. The concept of cognitive radio was first proposed by Joseph Mottola III in 1998. Since then, many cognitive radio projects have been executed. Cognitive radio is a form of wireless communication in which a transceiver can intelligently detect which communication channels are in use and which are not. It instantly moves into vacant channels while avoiding occupied ones. There are two main types of cognitive radio. The first type is full cognitive radio, also known as Mottola radio, in which every possible parameter observable by a network is considered. The second type is spectrum sensing cognitive radio, in which only the radio frequency spectrum is considered. Within the cognitive radio, it contains functions which are spectrum sensing, power control, and spectrum management. Spectrum sensing is used to detect unused spectrum and sharing it without harmful interference to other users. Power control is used to allow the cognitive radio network to access the frequency band of a primary user. The spectrum management is used to capture the best available spectrum to meet user communication requirements while not creating interference with primary users. The main goal is to have a software-defined radio that can evolve and in this case can have a fully reconfigurable wireless transceiver which automatically adapts its communication parameters to network and user demands. Now that you have a basic understanding of what cognitive radio is, the next slides will go into depth of how cognitive radio works and after talk about the benefits that cognitive radio brings and the challenges when implementing cognitive radio. The last slide will be an example of how cognitive radio can be used.
In a cognitive radio network, the primary user is a licensed user who controls a portion of the radio spectrum that they can then temporarily lease to the unlicensed secondary user. This process is all dependent on whether the primary user is active or inactive, because in most cases the primary user will not lease active portions of the spectrum to the secondary user. What this does is improve the efficiency of an active primary user as it will not be hindered by interference from a secondary user, and at the same time improves the efficiency of the secondary user as it will not be interfered with by an active but idle primary user. In order for this process to work smoothly and for the secondary user to be able to lease space on the spectrum, the efficiency of the primary user must be maximized through data limiting the incoming transmission of packets to the primary user so that it does not stay busy for extended periods of time. There are two main dynamic spectrum access models that apply cognitive radios and allow the cognitive radio to moderate a radio spectrum. The first of these models is the Opportunistic Spectrum Access Model, known by the acronym OSA, which appears in the figure to the top right. In this model, the cognitive radio analyzes the entire spectrum to find vacant areas of the spectrum that can be leased to a secondary user. The cognitive radio also facilitates the forfeiting of spectrum space by primary users and continually plays the roles of gatekeeper to the spectrum. When the cognitive radio detects a vacant space in the spectrum, it must perform modulation on the message signal in order to ensure that the incoming message has valid parameters that satisfy the spectrum space's requirements. The second DSA model applied is the Concurrent Spectrum Access Model, known by the acronym CSA, which appears in the figure to the bottom right. The CSA model, sometimes referred to as the underlay method, operates by allowing multiple secondary users a lease on the radio spectrum under the condition that the interference on the primary user is minimal and controlled. This allows cognitive radio networks to completely overcome the challenge of having to wait for idleness in the primary user's transmission in order for the secondary user to begin transmitting. For this model to function, the cognitive radio is responsible for limiting interference through modulation and filtering of the secondary user's signal transmission. To apply the models mentioned, a concept called spectrum sensing must be used by the cognitive radio. Spectrum sensing encompasses a wide array of techniques used in order for a secondary user to detect if a primary user is active or not. If it is active, then the secondary user needs to quickly disband from the system in order to prevent any possible interference with the primary user. For the OSA model, spectrum sensing is used to find vacancies by having the cognitive radio analyze interference and determine if the interference was from a primary user or not. This process is called primary transmitter detection. The most common way this is applied is through energy detection, where the signal is passed through a bandpass filter and integrated over a period of time. This integrated output is then compared to a known threshold value to determine an absence or presence of a primary user. This method is simple to apply, but has a high probability of error and suffers from the fact that it requires the cognitive radios to have a very low latency. For the CSA model, spectrum sensing is used to find interference from the secondary user transmitter. For this, the primary receiver detection method is used, where a node is placed at the primary receiver of the system. This node then gathers data and sends it to the cognitive radio, which analyzes the data and notifies the secondary user that it can become active or not.
Now moving on to the benefits and the challenges. Starting with the benefits. In 2002, the FCC came out with a report where it stated that most of the frequency bands in our spectrum aren't being used most of the time. Now, spectrum holes are defined as bands of frequencies which are not used by the primary user at a particular time and at a particular geographical location. And now with spectrum holes, there are three types: black spaces, gray spaces, and white spaces. Black spaces are occupied with high power interferers, gray spaces are occupied with low power interferers, and white spaces are free of interferers. Now, out of these three, white spaces are the most beneficial since it would allow a secondary user to utilize those free bands without causing any sort of interference to the primary user. Another benefit is cognitive radio's intelligent decision making. Since it's able to detect which channels aren't being used, this allows the radio to switch to the channel with the highest quality. Because it can move around, the overall quality of the service drastically increases, since it's choosing the frequency channel that will provide the best signal to noise ratio. Now looking at the picture on the right, we can see that the blue boxes are spectrums occupied by licensed users, and those red boxes in the middle are considered spectrum holes and for the most part white spaces. In those white spaces is where secondary users could access those unused bands without causing any interference to anyone around them. Now moving on to the challenges of cognitive radio. One major problem does appear to be radio jamming. Now this tactic utilizes machine learning to disrupt channels. Essentially what it tries to do is it will try to predict where there will be a successful signal. If it does detect the signal, then it will try to attempt to jam the signal going through. If it is successful, then the signal to interference plus noise ratio will start to deteriorate, as well as the bitrate error. Another challenge that comes with cognitive radio is that second users must be very careful when accessing these frequency bands. When they are connected to channels, they have to constantly be adjusting their signal in order to not interfere with the licensed primary users. If they're not careful, this could lead to a chain of disruptions within all the channels. Now, because there are so many channels being involved, security is also a big problem. Now, cognitive radios do come equipped with their own defensive mechanism, but it is possible for a user to make themselves appear to be the primary signal, which would, in fact, make it harder for those defensive mechanisms to detect them. Another issue seems to be simply how localized all the signals are. Because they are all in one place, this makes it easier to disrupt the overall channel. If for whatever reason a user was able to modify it, then they could essentially restrict anyone else from accessing the channel. Now, if we look at the image on the right, we can see two cellular devices in the top left corner, signifying the primary users. We can see a phone right in the middle that symbolizes the secondary user. Now we can see two attackers and a receiver. And the secondary user and the receiver are trying to communicate to each other, but there's two attackers that are attempting to jam the signal.
So an example of where cognitive radio can be implemented is during a space mission. Space seems empty and therefore seems like a perfect place for radio communication, but it is not. There are several interferences that can distort radio communication. These interferences can distort the materials of the antennas as it heats and cools. There are also low-level abundant radio emanations known as cosmic noise that come from distant quasars, the sun, and the center of the Milky Way galaxy. They are faint, but the sources can overwhelm a wireless signal. Now imagine a group of astronauts in space. As the space environment changes and the planets move relative to one another, the radio settings on the ground station, the satellite orbiting a specific planet, and the Martian lander will need continual adjustment. The astronauts could wait 8 to 40 minutes for mission control on how to adjust the settings. An alternative is to have the radios use neural networks, and common radio can accomplish these tasks. Its ability to learn from experience allows the radio to try out new configurations in new situations, which makes it ideal for space communications where the environments are relatively unknown, human intervention is impossible, and maintaining connectivity is vital. The figure to the right is an example of how several adjustments to settings is needed when traveling through space. And this concludes our presentation on cognitive radio.